In this video, we introduce logarithmic functions. And again, I suspect you've seen these in previous math classes, but they can be tricky. And we introduce them now because they're a very natural extension of an exponential function. Namely, it should turn out that logarithmic functions are the inverse function of an exponential function. So why don't you pause, copy this panel down, and then press play. All right, so we introduce logarithmic functions, as the inverse function of an exponential function. And you'll recall an exponential function was a function of the form b, some constant number b raised to the x power. B generally, well, b greater than 0. Right, now initially logarithms were developed in the 1600s and 1700s to help handle the massively large numbers that were cropping up as scientists were examining the orbit lengths of planets and trying to figure out, why do planets revolve around the sun? And what shape do they take? And can we figure out if that shape is telling us the reasoning behind why they orbit? Okay, so we're talking like Kepler, Newton, Van Gogh's. There's a famous telescope creator and scientist named, forget her first name, but Madame Herschel in England. Okay. All right, so some vocabulary. I would say, I should have written this down. This expression, I would read it as log base b of x equals y. That's how I'll say it, log base b of x equals y. This is a logarithmic function. X is my input and y is my output. Now, it turns out this logarithmic function has an equivalent exponential expression. So if I tell you log base b of x is equal to y, that is equivalent to saying b raised to the y power equals x. So that's the exponential form that's equivalent to this logarithmic form. B raised to the y equals x, right? That's the exponential form. So let's mess around with that. I should be able to go from logarithmic to exponential or from exponential to logarithmic, okay? So here's a logarithmic expression. Log base 4 of 64 is equal to 3. And it's equivalent to 4 raised to the third power equals 64. And if you check, that's true. 4 squared is 16, 4 cubed is 64, okay? So if you don't like thinking about it as a log, flip it over and think about it as an exponential expression, okay? Now, we should also be able to go backwards. So here's an exponential expression, 3 to the 5th equals 243. You can check 3, 9, 27, 81, 243. Okay, so I didn't screw it up. I can flip that into a logarithmic form. 3 will be the base of my log. 243 will be the x value. And the 5, the power, is the y value in the logarithmic expression. So b to the y equals x. The y, the power, came back as the y value on the other side. The b became the base, so 3 became my base. And the x value here gets sucked into the logarithm. So that 243 gets sucked inside the logarithm. So log base 3 of 243 equals 5. And this kind of illustrates what those astronomers were after. 243 is a big, huge number. I don't want to deal with it. I don't want to add it and multiply it to other things. If I hit it with a log, it becomes a much smaller number, which is arithmetically much easier to handle. We'll talk more about that aspect later. All right, but upshot. Logarithmic form has an equivalent exponential form, so the exponential form has an equivalent logarithmic form, and we should be able to pop back and forth between the two. All right, let's do some more examples. All right, so why don't you copy these two examples down and then I'll crank through them. So in both cases, I'm trying to evaluate the value of a logarithmic function, okay? So let's start with this one. The log base 2, 256. I don't know what it equals, so let me just call it y. It's my output of this function, and I'd like to know it, right? The input was 256. The function was the log base 2 of x. I'm going to flip this into its exponential form. So that logarithmic form is equivalent to me saying 2 to the y power has to equal 256. Okay. So I flipped it to the exponential. And the reason I did that is I think I might be able to figure out the power of 2 that gets me to 256. So there's two ways to do this. I guess I'll do it just one way though. So 256, let's think of that as a power of 2. 2 squared is 4, 8, 16, 32, 64, 128, 256. So I believe 256 can be written as 2 to the 8th. I want to check my math though. 2, 4, 8, 16, 32, 64, 128, 256. Yes, 8. Okay, so I flipped it to the exponential form, and then 256 is the same as 2 to the 8th. So if 2 to the y is equal to 2 to the 8th, well, that must mean that y equals 8. Okay, so I think I've got the answer. Log base 2 of 256 is equal to 8. Right? Because 2 to the 8th is 256. All right, let's try it again with something a little more unusual. Ooh, I got a fraction there. Okay, so I'm going to go the same way though. Log base 5 of 1 over 625 is equal to some number y that I don't know, but I would like to. Okay, I am going to flip this into its equivalent exponential form. So 5 to the y is equal to 1 over 625. Okay. And now let me just pick on 625 like I picked on 256. I think 625 is a power of 5. So let's check it out. 5 to the first is 5, 5 squared is 25, 5 cubed is 125, 5 to the fourth is 625. Okay, so I think I could replace 625 with a 5 to the fourth in the denominator. So I have 5 to the y power is 1 over 5 to the fourth. And I could bring that 5 to the fourth out of a denominator by writing it as 5 to the negative 4. So I think what I've just determined here is that 5 to the y equals 5 to the negative 4. Well, so then y has to equal negative 4. So I think we've discovered the y value, or the output of this function. Right? So to summarize, log base 5 of 1 over 625 is equal to that y value, which we now know is negative 4. Because 5 raised to the negative 4th power is 1 over 106, 1 over 625. Okay. All right, so let's get slightly more formal here. And when I say that, I should next appear on screen with like a tie on or something. All right, so here's a more of a formal definition of a logarithmic function. And some things have not yet been explained, but we're going to have x's greater than 0. We're going to have b's greater than 0, and b better not equal 1. So with those restrictions, the function y equals log base b of x is equivalent to e to the y equals x. So that's summarizing what we did over there. And for the function log base b of x, where b is greater than 0 and b doesn't equal 1, the domain is going to be x's are greater than 0. We cannot handle a negative x value. We can't handle 0 as an x value. And our range is going to be all real numbers for this function. And that's true no matter what the b value, the base is, as long as the base is greater than 0 and not equal to 1. All right, so you might ask, why can't this logarithmic function handle a negative number for the input? So let's look at the logarithmic function log base 3 of x, and let's try plugging in a friendly negative value, like negative 9. I mean, 3 squared is 9, so it seems friendly. Let's try and evaluate this. If I say it equals y, just like we did in the last two examples, I can flip this to the exponential form, and that would be 3 to the y power equals negative 9. And now we see a problem. There's no power of 3 that makes it negative. I mean, 3 to a positive power, 3 to the 8th is 3 times 3 times 3, 8 times. It's all positives. 3 to a negative power, like 3 to the negative fifth, 3 to the negative fifth. Well, that's just 1 over 3 to the fifth. And 3 to the fifth is positive, so 1 over 3 to the fifth is positive. So what I'm saying is 3 to the y is greater than 0 for all y. So there's no way 3 to the y could ever be a negative number. So I just can't calculate log base 3 of negative 9. There's no answer to that. So we would say it does not exist. Okay. Similarly, why couldn't x equal 0? Well, imagine having a 0 there. 3 to some power equals 0. Well, 3 raised to any power can never be 0. Like 3 to the 0? Nope, that's 1. 3 to a positive power? Well, that's bigger than 3. 3 to a negative power? Well, now we're 1 over 3 to powers, and those are still non-zero numbers. So my x values, they can't be negative and they can't be 0. And then if I had a base equaling 1, that'd be crazy talk. Log base 1 of a number, log base 1 of 5 equals y. That's equivalent to saying 1 to the y power is 5. There's no power of y that sends 1 to 5, right? 1 to any power is always just 1. It's the most boring, stupid logarithmic expression ever. So I can't have base be 1. And if the base is a negative number, oh, we really get messed up. Because negative bases to powers just start flipping and alternating, going all crazy talk. We don't want to deal with that. So we restrict our bases to greater than 0, other than 1, and the domains are forced on us. The x values are greater than 0. All right, the last panel, some special cases, nothing too weird here, but there's 2 logs we use a lot, so we give them special names. The first is the function, the log base 10 of x. We call that the common log. We like 10, and 10 to powers is really good. And we use it so often that we'll drop the base when we mean log base 10. So if you just see log of x, it's assumed you know that it means base 10, okay? Similarly, we've got this special number e, which we'll talk about why it's special in the future here, but it's about 2.7182 ... It's like pi. It's a special number. It's got really cool properties. It's always about that. It's irrational. It never ends, never repeats, blah, blah, blah. But when we use log base e, we will abbreviate it as ln of x. So when you see ln of x, it is assumed you know this means log base e. And we call this the natural log because it is used to model natural processes. Okay, so let's just test this out, see how it goes. Let's determine the common log of 1,000 and the natural log of 1 over the square root of e, right? So common log of 1,000, if I want to know what it equals, I'll just set it equal to y. And I know in my head that the common log is the log base 10 of 1,000. And I'm just going to flip it into its exponential form. So 10 to the y equals 1,000. And I know 1,000, oh, that's a power of 10, right? There's 10 to the first is 10, 10 squared is 100, 10 cubed is 1,000. So 1,000 is 10 cubed. So I know that my power is equal to 3. So the common log of 1,000 is equal to 3. Because 10 cubed is 1,000, right? Let's play the same game here. Natural log of 1 over the square root of e is equal to y. So I can think of that as log base e of 1 over square root e equals y. I can flip this to its exponential form, e raised to the y power equals the x value, 1 over square root of e. And now I'm just going to muck around with 1 over the square root of e and simplify it to a form of e to a power, okay? So I know the square root is the 1/2 power. And I know if I've got an e in the denominator, I can bring it up to the numerator by making the power negative. So 1 over the square root of e is the same as e to the negative 1/2. All right. Well, if e to the y equals e to the negative 1/2, then I've got to have y equals negative 1/2. Or another way, or in summary, the natural log of 1 over the square root of e is equal to this number, -1. Okay, so we're gonna do some practice problems in class. Hopefully this is ringing some memories in your head from days gone by.